I'm very sorry not to be with you all during this conference, but thank you for allowing me to present in this mediated manner. I look forward to discussing the paper with you during the question and answer period by Skype afterwards. So I'll be talking about physicalism and the conservation of information. I'll try to argue ultimately that physicalism comes apart from a set of commitments with respect to the conservation principles, etc., and should be thought of as a distinct set of commitments to basic meta level commitments or constraints in physics. The physicalist favors some books of the world over others. So in our time, physicalists will reject books whose narratives violate physical conservation principles. These principles serve as meta-transformations that govern our physical reasoning about possible transformations from one state to another. So to accept these or any other meta-level constraints involves reducing the set of possible ways things could be, let's call them possible books of the world, from, for example, the space of logically possible books to the space of what we might call extended nomologically possible books of the world. So when we talk about these states and transformations that a metaphysical theory provides, we could think, for example, of what Peter Railton has called the complete explanatory text of that metaphysical view. So nomologically possible worlds, of course, are those which obey the same laws of physics as the actual world. The set of extended nomologically possible world would be those containing or those obeying some meta principles of physics, like, for example, the conservation principles. But we could include in that set worlds that don't contain the same physical laws as our own. So as long as they comport with these constraints, let's say the conservation principles, they'd be included in this set, but among the possible ways physics could be are physical theories that don't look like the physics of the actual world. So we can take conservation laws in physics as ruling out certain kinds of transformations, and the ones that remain in, we'll call those the extended nomological set of possible worlds. So conservation principles then are simply features of our physics that are held to be invariant over time. And there are a variety of ways that a book of the world or a metaphysical theory might exhibit this kind of invariance. For example, given some set of n possible states, as we have on the slide, we might be concerned with the set of possible cycles through those states which preserve information and include all states. So let's call these one-cycle books. So if we had 4 possible states and a constraint that our book contain a single circuit and conserve information, so for example there would be a single circuit of 4 states conserving information, here's an alternative, then we'd have the following books of the world. We'd have these 6 possible ways that things could go. So if they're given some n set of states, the set of possible cycles through the states which preserve information and include all the states would be n minus 1 factorial. So in this case there are 4, so there'd be 4 states, so there'd be 6 possible ways through all 4 states preserving information. These books tell a story in which an agent at any step in the successive unfolding of the system would, in principle, be able to determine the entire sequence of steps in the history of the system. So even if an agent didn't know how many possible states there are in its world, and given knowledge that the universe behaves like a one-cycle book, the agent could be sure that there are n minus 1 factorial sets of possible books. Why would, though, a metaphysician confine herself to one-cycle books of the world? Well, the advantage of these books, of course, is that given knowledge of a single state of the system at an instant, an agent who has access to the books would know everything about the system. Now, ordinarily, physicists are not that optimistic, and neither, I suppose, are physicalists, philosophers. They recognize instead that the conservation principles permit the existence of independent systems. Independent subsystems, rather. So what do we mean by subsystems here? Well, in addition to the 6 cases we described above, we could add cases like the following. So we could imagine alternatives where there are some systems that obey conservation principles but involve distinct cycles, distinct subsystems. So here in this case, we have, let's say, from 1 to 2, or from A to B, and from C to D, etc., etc. Now, if we admit multiple circuits or multi-cycle books, then the number of transformations that preserve information is n factorial, where n is the number of states in the set. So if we're looking for books of the world then that obey conservation principles and that have, let's say, only 4 states, then we'd have 24 or n factorial possible ways that things could be. But let's say we didn't care at all about conservation principles, and then we would be free to drop any restriction, and then there'd just be the combinatorial, well, a space of logically possible combinations of states, and there'd be n to the power of n possible transformations. And so in a system of the kind we were just looking at, there would be all kinds of books of the world that, if our only constraint were logical possibility, we'd have all kinds of violations of conservation principles of various kinds. These would fall outside of the set of extended nomologically possible worlds. And as we begin to read one of these forbidden books of the world, we quickly encounter a phenomenon known as transients. So a transient state is simply one that's part of a sequence of states with a first member. So if the state is a part of a sequence of states, a finite sequence of states that doesn't have a first member, then what we say is that state is in a cycle. And of course, transients would be anathema to physics insofar as they fail to be deterministic into the past. So the laws of physics as we know them are symmetrical or time reversal invariant. And physicists say that laws are invariant under time translation. Of course, transients are not. Any system whose possible states and transformations allow for more than one arrow in or out of states, or whose states lack an in arrow, we'd say that these systems have or contain transients. Now, theoretical physicists might not like transients, but in nearly all other scientific contexts, they're ubiquitous. For example, any science which uses computational models, large parts of engineering, etc., will have to find some way to cope with transient states. Now, any book of the world that is generated by computational modeling then is likely to exhibit behavior that doesn't comport with conservation principles or doesn't admit of reversibility in the usual manner. So in cellular automata, for example, transients will appear in most runs of the system, and systems that exhibit reversibility or conservation will be a tiny minority of the possible legitimate mechanisms or legitimate cellular automata books of the world. Steve Wolfram, for example, showed that among the 256 elementary cellular automata with 2 colors and nearest neighbor rules, only 6 exhibit a reversible output. So irreversibility then would be a characteristic of most cellular automata outputs. And it's also worth considering that, or noting that cellular automata are just a tiny subset of the set of algorithms that we might want to consider for one reason or another. Anyway, we'll hopefully talk a little bit more about that during discussion. So in systems like cellular automata, initial states, and this is a diagram from Andy Wunsch or Wunsch. Um, initial initial states are going to follow. They're going to follow transition rules of some sort, such that they'll tend towards an oscillator. And this means that after some finite sequence of steps, the cellular automaton will enter into a repeating cycle of states. So note that these systems don't preserve information concerning the past states of the automaton. So in this handy drawing here, we can see that it might begin with some state B. I'm pointing to it with the cursor. And then following the rules, it'll head off into some other state in the state space. So let's say we've got a state A following the transition rules or the transformation rules of the automaton, goes to B, goes to C, etc., etc. But there might be a variety of paths to get to state B, such that from state C, let's say there was only one way back to B, but there might be a variety of ways to have gotten to B other than A. That information, of course, well, not of course, but in this case, will be lost when you get to C. So it might be the case then that we follow a sequence of states, and the trajectory, as will generally be the case in cellular automata, resolves to some cycle or sequence, or an oscillator, let's say. So after a finite sequence of steps, then the cellular automaton will enter into a repeating cycle of states. It might just be, all off, so it stays in some state, X, 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 X from there on. Or it might oscillate in the familiar way. Okay, so earlier we saw how conservation principles might constrain one's choice of books of the world. But notice how there could be a denizen of one of these oscillators, let's say an agent who lived in one of these oscillators, whose universe is the result of fundamentals organized according to the algorithm of a cellular automaton. But this inhabitant of the oscillator might be in a position to propose a book of the world such that she thinks that she's accounted for the entire past, present, and future of her universe, because her universe will take the form of this oscillator, without, or while she ignores, let's say, the possibility that her present cycle, this oscillator she lives on, is compatible with having come into existence via this transient state. So returning to systems then that are constrained by the kinds of conservation principles that interest physicists and physicalists, we recognize that books obeying conservation principles include what we call multi-cycle books. So as we saw above, or previously, if we include isolated loops and subsystems in a system of n states, the number of transformations that preserve invariance will be n factorial. So to summarize then, this n factorial set of books would include transformations with discrete subsystems, but it would also, well, it would primarily, the point is that it would exclude transients of the kind that we've just considered in cellular automata. So given that there are n factorial systems of fundamentals or systems of sets of books, some of which can have distinct cycles or subsystems, let's consider an example of their behavior. So when we think about these possible physically law-abiding subsystems, it can be fruitful to think of them as networks with their own specific sets of laws. So at this stage we can consider networks written, we'll consider two networks on the screen here, written in a book, a single book, which we'll call the Book of Phi. So networks 1 and 2, pictured here, are a representation of the story told by Phi. At this stage, one might ask whether it's legitimate to understand these as isolated, law-governed systems, or as consequences of the laws governing some system that's composed of networks 1 and 2. So in this case, let's simply stipulate that phi describes two distinct oscillators, pictured here, or networks, and that phi is also consistent with conservation principles. So phi doesn't stipulate or specify any interaction between the two networks. So for example, imagine for the sake of the present argument that one's interested in possible ways that these two networks could interact. So this would be, let's say, a metaphysical question. So while no such rules for interaction have been included in the story that's told by phi, one could ask whether phi excludes interaction or simply leaves interaction undetermined. So does this entire picture here, this network, let's go through it. So does this exclude possible interactions, or does it somehow simply not include possible ways these things could interact, these two networks? So from the physicalist perspective, as we'll see, the only books worth having are complete books. And therefore, a physicalist will assume that interaction of networks 1 and 2 is excluded by phi. Now the methodological problem with the physicalist's view of fundamentals should be starting to become apparent. So when building a set of fundamental metaphysical principles, surely we can't simply claim completeness by specifying the fundamentals and then adding the condition that there are no events other than the events determined by the fundamentals. This would almost be as bad as claiming the completeness of Principia Mathematica simply by stipulating that it captures all the truths of arithmetic, and that no other truths of arithmetic are, that none of the truths of arithmetic are unprovable in the system of Principia Mathematica. So this would be a clause that one might attach to one's account of the fundamentals that says, and it says about the system, it gives the rules, it says it's A, B, C, and D, governed by these rules, and that's all there is. So it's an and that's all there is clause. So when we define phi for any sufficiently complex or interesting cases, physicalists who are motivated by a kind of worry about emergence and who have this anti-emergentist concern shouldn't simply forbid the interaction of the subsystems by fiat insofar as they want to avoid begging the question against emergentism. So I'll provide a more extensive defense of this claim below. So for now, and solely for the sake of argument, let's assume that there are possible interactions between, let's say, our two networks here that are contingent with respect to phi. This would mean, of course, that phi was an incomplete book of the world, that it didn't give the full narrative of the whole deal. So for the purposes of the present argument, the source of why it is or how it is that these two things interact isn't important. For now, and solely for the sake of argument, let's assume that there are possible interactions between the two networks that are contingent with respect to phi. This would mean that phi was an incomplete book of the world. So for the purposes of the present argument, the source of the interaction rule isn't important. So for example, given our two networks described above, we could arbitrarily introduce some new rule, call it the interaction rule, which gives us a new book, and the book is phi star. So here's the interaction rule, it's just popped in. Okay, so phi star, pictured here, is a new book which results from adding interaction rules to phi. So beginning with A in network 1 and W in network 2, let's consider the way that things unfold in light of the interaction rules specified. So notice before it was clear that A would go to B, B would go to C, C would go to D, D would go to A. W would go to Y, y would go to x, x to z, and z to w. Okay, once we introduce the interaction rule, we've of course jerry-rigged this so that something interesting will happen. So let's take a look at how this would run. Let's start the run. A and W. A goes to B. W goes to Y. Everything so far so normal. B goes to C. Y goes to X. But then when we get to D and Z, we have the rules for interaction kicking in. So the interaction rule kicks in, and then we get D going to B instead of going to A, and Z going to X instead of going to W. So as we've seen up here then, everything was fine till we got to DZ. When we got to DZ, interaction rules kicked in and bumped us to this new state, BX. Let's continue. So far we're engaged with the rules internal to the network, as we've previously seen. Now B goes to C, X goes to Z, C goes to D, and Z goes to W. At this point, we've engaged another interaction rule down here, DW. So we say that if it's DW, then D goes to C and W goes to Y. C goes to D, Y goes to X, A goes to, and then D goes to A, X goes to Z. But now the interaction rule kicks in again, sending A to B and Z to Y. A goes to B and Z goes to Y because of the action of the interaction rule. So now, of course, B will go to C and Y will go to X. No surprises. And then C will go to D and X will go to Z. No surprises. But notice now we've gone back to this stage, and this has introduced our little transient here, as we'll see. Okay, so once we get to this point, once we get to DZ, once we get back to DZ, let's see, there we go. Once we get back to DZ, now we'll never again revisit this ABC WYX sequence. So now we'll continue cycling from DZ through to DZ here, and we'll end up with a new set of rules such that this is the case. So now we have rules for the system as a whole. And so this would then be a description of the rules once we've overcome the transient and once the system as a whole has settled into its oscillator. Now what happened to AW? Well, the interaction rules here have introduced transient states. And clearly if we have interactions, then we're going to end up with these kinds of transient phenomena and with information loss. So in some sense, so what we're saying is that interaction can introduce information loss in systems like this. If there is genuine interaction, then we can have the introduction of transients. And notice that once we have the interaction rules in place, then things could look, remember this is sort of like when we're here, it's like being one of those agents on the oscillator, right? So we think we've basically got the whole story because we'll never go back to AW. We'll never end up back here to ABC, WYX, to this particular configuration. So we're generating new patterns subject to generalizations which don't hold or are even in violation of the rules given in the networks in isolation. So here we see that we're going to have a violation of the ABCD rule via the interaction. But that's actually less important, less interesting than the appearance of transients after interaction and the information loss that comes along with that. It's also worth noting that if we started with different starting points, we'd have different sets of transients or potentially no transients. If we'd started with some starting points, like for example, we started with AW and the other one, but here we could start with something like, I don't know, well, we could set it at a different starting point like X, so AX. Then you'd see different sets of transients or potentially no transients. So let's see. Starting at BZ, for example, yeah, never activates our rule of interaction. So what do we want to say about toy cases like the one we've just looked at? Well, I mean, clearly a physicalist won't permit or can't permit interactions of the kind we entertained in the case before of phi star. So the physicalist then has to make sure that there are no interactions of this kind in the future. We have to make sure, or at least the physicalist has to make sure, that we're never going to get the appearance of transients by interaction. And so in one sense, the physicalist has to block interaction per se. So what are we saying? We're saying that all subnetworks, even though they look legal, they look like they're in compliance with conservation principles, and these kinds of systems with genuine subsystems may be in compliance. They form a large part of the extended nomologically possible set of worlds, but they're not permitted given the physicalist's additional "and that's all there is" clause. So, that price might be worth paying if it really did block emergence and if it genuinely provided completeness for physicalist fundamentalism. But unfortunately, for the physicalist, it fails to do so. So, of course, it's logically possible that we could live in a world that's accurately accounted for by a finished physics with a set of functions that determine the behavior of the system, that are deterministic in the forward and reverse time directions. But it's also possible that these physical laws would be the product of processes like those described in phi star. So if so, then there may have been a history over the course of which there was at least one transient state. As we've seen, it's possible, therefore, that there's no way to recover this history from exhaustive knowledge of the present laws of nature. And these laws of nature then may have emerged from a different set of laws via a simple process whose character can't necessarily be gleaned from the current laws themselves. The kinds of processes I'm thinking of here are entirely mechanistic. There's nothing supernatural here, as we've seen before. Yeah, so we could always say then, we could call this the skeptical challenge to physicalism, that any law-like system, any claim to having a complete system is open to the challenge that, that system could be the result of a transient. Now, more constructively, we want to say something like, well, this isn't just a skeptical challenge, that, if we accept the possibility of interaction, then maybe we can discover ways of isolating subsystems and studying interactions in ways that allow us to discover or reconstruct the mechanism by which a new system emerges. And of course, this shouldn't seem particularly strange. I mean, this is basically what we do. Engage in controlled experiments. We attempt to isolate and attempt to screen off certain conditions, etc. So acknowledging interactions and then attempting to control interactions is part of what we do and gives us the prospect of rebuilding the process that led to the resulting system. My general view is that we should expect the possibility of nomologically contingent interactions between subsystems. We should expect interactions generally. In such cases, we're going to find instances where the joint action of, let's say, two systems is such that the result is emergent with respect to those two systems. So in order to block this contingency, the physicalist might posit some third, more fundamental principle or system, And if this third law subsumes the generalizations of the initial two systems, we could try to comfort ourselves by reverting back to some one rule or one cycle scenario. However, as we've also seen, even if this one rule scenario really does represent our current situation, it fails to block the skeptical challenge. And as we'll see in the next section, I think this points to some more basic flaws in physicalism per se. Now, as David Papineau pointed out, the dominance of physicalism among philosophers of mind, for example, is largely due to a set of empirical considerations, or sort of, let's say, scientific common sense style considerations. Physicalists basically noticed that over the course of recent history of science, appeals to non-physical factors in scientific explanations have been associated with degenerate research programs and dead ends. So by contrast, reductive strategies and physicalist ontological assumptions have been associated with fruitful and progressive research programs in the natural sciences. And of course, contrary to what Jerry Fodor said, the denial of physicalism doesn't involve any obvious logical contradiction or conceptual error. Daniel Stollier makes this point in his recent book. Denying physicalism isn't philosophically absurd, but it does seem to put one in conflict with science and scientifically informed common sense. I don't think that's the case. I think we can preserve all of the epistemic virtues that we associate with science while giving up on physicalism. And I suspect even we might go a little farther and say that many of the vices we hope to avoid, we risk succumbing to those if we cleave too fervently to physicalism. Let's see. So there have been many prominent criticisms of the inference from the empirical success of reductionism to the conclusion that physicalism provides a complete ontology. The most famous, of course, I think the most direct is, I should say the most direct challenge to physicalism is Hempel's. Hempel, as we know, argued that while physicalists regard physics as their guide to determining the correct ontology, they clearly don't mean to commit to the ontology given by the current physics or the physics of the past, because physics of the past, of course, is false or has falsehoods. Contemporary physics looks like it's also containing falsehoods. Certainly has a very important contradiction at its core. We could talk about that in discussion if you'd like, but certainly by induction we should expect that contemporary physics is going to be false, at least contain some falsehoods with respect to ontology. So the choice then, Hempel says, is between committing to an ontology of false or probably false theories, given by probably false theories on the one hand, or of committing to the ontology of some ideal finished physics, some future physics when we work out all the kinks. But of course the trouble with committing to that future physics is that for all we know it might include qualitative mental states or ghosts or something else as fundamental. So relying then on the history of science as evidence for the completeness of a physical ontology isn't a strategy that guarantees success for physicalists. In contemporary philosophy, of course, there are a whole slew of arguments from concerning qualia, and I'll leave those. Those are familiar. And, traditionally philosophers have responded to physicalism in various ways, arguing, for instance, that the explanatory role of higher level generalizations is such that these can't be reduced to some lower level set of facts without losing explanatory power. That's a standard non-reductive physicalist argument. Some philosophers have thought that also has bearing against physicalism. Alternatively, some philosophers like Louise Antony pointed out that there are features of some concepts that require their bearers to have appropriate historical properties. insofar as they connect with traditional criticisms of physicalism. The kinds of things that I've been saying here have some connection, I think, with Louise Anthony's arguments, maybe contribute to her line of argument. Whenever encountering these kinds of objections, the physicalist's response to specific examples of non-physically determinable differences, let's say, is to either provide reasons to believe that these differences are unreal, or to claim the truth of the sentences mentioning these differences can be explained via some more basic supervenience relation on the really real action at the micro level, so that those basic facts explain all the facts. Physicalist completeness claims are directed to present and future states, such that physicalism can't exclude the kinds of transients we've discussed here in this paper. Nor can physicalism do justice to the kinds of historical properties, I think, that Louise Anthony and others have noted. Now, so as such, physicalism can't exclude the possibility that the physical fundamentals themselves are emergent features of some more fundamental metaphysical principles. And as we've seen, it's possible to grant completeness with respect to present and future states and still allow for the possibility of emergence having happened in the past. So the argument that I've been presenting today provides a plausible, I think, and naturalistically respectable way of making sense of the possibility that there are these historical properties that are relevant in ways Anthony describes, for which physicalist fundamentalism can't account. So, of course, she was talking about properties like being someone's spouse or membership in a species, etc., all of which are historically determined. I'm talking about something different, but I think there's still some important connection. So, but even if we dismiss the possibility of transience as an exotic, skeptical worry about the past, which, that might be the natural reaction, the physicalists will still have to find ways, as we've seen, to exclude interaction, to exclude these contingent interactions in the future. Insofar as it's complete with respect to the future facts, physicalists must exclude nomologically contingent possibilities of interaction whose results lead to new generative fundamentals. So in other words, only events that are a necessary consequence of the fundamentals can take place. However, there's a real price to be paid for completeness with respect to the present and future, too. So as we've seen, one way of blocking nomologically contingent future interactions is to claim that possibilities for interaction are already somehow accounted for in the fundamental physical properties. So in this view, then, we simply assume that the fundamentals determine the outcome of every possible future interaction, such that there are no nomologically contingent interactions. And this effectively eliminates the possibility that there are systems with subsystems that obey conservation principles, but this, however we go, however we understand that, the restriction on the space of possible ways nature could be here is motivated solely by the threat of possible future interactions that are nomologically contingent. So common sense tells us, of course, that interactions can change the character of their participants, and that interaction is a ubiquitous part of the natural world. And it's common for emergentists to argue that participation in structural wholes can change the nature of the parts of those structures. Sandra Mitchell's recent book and elsewhere contains examples of that kind of phenomenon. In order to rule out this kind of novelty, and especially the possibility that structures might exhibit synchronic downward causal powers, fundamentalists have to include all the possible fates of the constituents in the fundamentals ahead of time. And I take it this is what Shoemaker tries to do in his discussion of emergent properties. So in effect, each part contains within itself some feature that makes it determinable how it will be in all possible states of affairs and interactions sort of a Leibnizian monad style setup. So on this view then, physical properties can't be permitted any interaction not already determinable given the fundamentals alone. So while it appears that there could be worlds with distinct subsystems governed by conservation principles, the physicalist regards them as only apparent possibilities. In fact, such worlds only appear to have distinct subsystems. They are actually coordinated by some more basic single cycle book. Some more basic single rule. I think here the trouble with physicalism is evident. It's that it excludes too many naturalistically respectable kinds of worlds.